it in person, but I wish I could have made it in person, but I unfortunately have to teach in about 45 minutes and couldn't get out of that. So today I'm going to talk a little bit about Bayesian Additive Regression Trees. And specifically, I'm going to talk about sort of a frustration I've had with them for a number of years. And that's how they deal with categorical predictors, namely one-hot encoding categorical variables. And what I'm going to argue today is that the way that they do this is deeply unsatisfying, both conceptually and practically. And so I'll introduce a class of priors that sort of fixes the issues that I find with the way that BART and tree modeling in general treats categorical variables. So to kind of set up the motivation for this, over the last several years, a couple of colleagues and I have been really interested in modeling crime data in the city of Philadelphia. So Philadelphia is divided into about 384 census tracts. And within each census tract, we actually have we actually have data of all of the reported crimes that happen in the tract every month. And we have data going back to sort of 2006. And so what we're really modeling is sort of time series that are each sort of evolving at different spatial locations. And when we look at our data, what we find is that, when we take the average of the sort of the crime levels in each census tract over this time window, we find that there's a really complicated spatial pattern. Namely, there are regions of spatial smoothness where sort of adjacent tracts have very similar crime patterns, not only in the mean levels, but also in sort of the entire trajectory of these time series. But there are also a lot of spatial discontinuities. And these discontinuities can occur across sort of well-known physical landmarks like rivers and parks, but they can also occur across sort of less visible boundaries that are sort of formed, or they sort of coincide with differences in sort of socioeconomic and demographic differences that really have been sort of created as sort of byproducts of historically discriminatory housing policy. So one of the things that we came to this project doing is we said, okay, if we're going to model these data, we really need something that we really want a model that could ideally adapt to the spatial smoothness and borrow strength spatially across tracts that are really similar, but not over smooth crime forecasts across places that are different. And we thought this was going to be really challenging. And so our ideal model would be one that would sort of allow us to make sort of individualized forecasts of the crime densities in each census tract, but still allow us to borrow strength in interesting ways. And one of the challenges is that the temporal trends in each tract are different. There's sort of a lot of examples around early 2020, where in some census tracts, crime sort of fell off precipitously, but actually increased in others. And so we're thinking, okay, there's going to be some nonlinearities in time, and there really are some interactions between time and space. And so one of the challenges is that if we were going to write down a parametric model to try to capture all of this, it'd be almost impossible to specify it correctly a priori. And so this difficulty, and maybe to sort of set it up, what we'll do is we'll model our data as sort of, the crime density in tract V at time t, we'll model as some normal realization around some unknown function that takes as argument both the census tract label and the time index. So the census tract label is going to be a categorical variable. And the difficulty is that, modeling these data realistically, writing down the functional form of this function is actually quite hard to do. It's not enough to just sort of have a single time trend and sort of a spatial random effect that would be too smooth. What we really need is something different. And this got us to think non-parametrically. That is, what if we could just sort of not write down pre-specified functional form of this function and just kind of let the data inform how we model it? And so from this perspective, BART comes out to be sort of a really compelling approach. It's a highly flexible non-parametric regression tool. It's over the last decade or so, it's had a lot of empirical success. You get generally excellent predictions and uncertainty quantification. And you can do it in a way that's really easy to use off the shelf. Often to use BART, you don't have to specify the functional form of the function you're trying to model. You don't have to do any hyperparameter tuning. In some sense, all you have to do is load your data into sort of a design matrix and a response column. And in R, it's enough to call something like the WBART function on X and Y. That's all you have to do, and you generally get really good predictions. So we said, okay, great, let's just throw BART at this problem. And yes, we have a function that depends on a categorical predictor and a time index. And in some sense, in principle, this isn't a hard problem. Default implementations of BART just do the usual thing where you take a categorical variable that has lots and lots of levels, and you one-hot encode it. You create a bunch of binary predictors. We do this in our linear models classes. We do this with a lot of statistical software. And you just treat these binary indicators, one for each census tract, as a new variable. And this is deeply unsatisfying, it turns out. For one thing, this sort of indicators lose the adjacency structure. They lose the spatial structure of the sort of the problem at hand. But there are also other sort of more fundamental problems. And so today what I'll do is introduce a regression tree prior that sort of obviates the need to one-hot encode your categorical variables when you're doing things like BART. It'll allow us to split on network structured categorical predictors. And we have I would like to say, a relatively easy to use package. It just went live a few days ago. And so I'll encourage you all to check it out if you have the time. So to get into it, BART is a sum of trees procedure. The idea is that you have some unknown function. It might depend on lots and lots of variables and complicated interactions. And the point is you're going to approximate this function using a sum of regression trees. And so what's really key to BART's success is the prior that it places on these regression trees that really heavily regularizes them to be relatively shallow and not explaining too much variation. You regularize to weak learners. And the way BART works is it writes down a prior for trees that takes 3 steps. So in the first step, you're going to generate a binary tree using a tree topology with a branching process. You start from a root node, you flip a coin, you decide to grow that root into 2 children, you visit each child, you flip another coin to decide to keep growing. And to ensure this process sort of terminates, BART sets its prior in a way that the probability of growing past a certain depth decays quadratically. So this is kind of like a Galton-Watson process with a sort of an adaptive probability of growing. And so the idea is that you'll generate a tree structure, say like the one that's shown here. And then what you'll do is you'll go around to every non-terminal node of the tree and you'll decorate it with a decision rule. And so you might say, okay, I'm going to pick a variable, maybe the first coordinate, and I'll decide that it'll be, if it's less than 0.5, I'll go to the left. And if it's greater, I'll go to the right. So this is sort of a standard decision tree. And BART does something very simple. It a priori will pick what variable you split on uniformly. And then it will sort of look at the values of that variable that are available at a decision node. And it'll just draw a value of the available values uniformly to form these sort of cut points. So the idea is that maybe at the root, you'll look at an x, and if its first coordinate is less than 0.5, you'll go to the left. And when it comes time to pick the decision rule at this node sort of here, you'll say, okay, well, all of my first coordinates have to be less than 0.5. So that'll determine sort of the set of values that you can split on. So BART sort of draws these sort of uniform decision rules that are sort of axis aligned. And then at the end, you decide, okay, once you have the decision rules, you decorate the tree again by deciding what the value the tree will take on. And the prior is usually something conjugate. And so what ends up happening is that this prior, regression trees are nothing more than piecewise constant step functions. And so what I've done is I've generated a tree from the BART prior. It's shown on the right. And on the left is sort of the corresponding piecewise constant step function that corresponds to the tree. So if you take any point in this unit square, you start at the root and you sort of follow a decision path down, you sort of follow the decision rules down to one of the leaves, you end up in one of these things and you output a mu1 or a mu2. And what's kind of interesting is that every decision tree or every regression tree that's produced by the BART prior corresponds to a piecewise constant step function. That piecewise constant step function sort of partitions your input space into these axis parallel rectangular boxes. And it turns out that every such partition can be represented with a tree. And moreover, every such partition gets positive prior probability according to the BART prior. And so this is a really good full support property. What it means is that BART has this incredibly vast representational flexibility because it allows you to use just about any step function that you want to estimate the function of interest. And this is true when all of your predictors are continuous. When they're not continuous, when we have categorical predictors, the story is much worse. And to illustrate this, imagine we were sort of doing our crime modeling, but we didn't use the time index. We just tried to model using the categorical variable encoding the location. What ends up happening is that BART will say, okay, the default implementations will say, okay, you've got a categorical variable with lots and lots of levels. Let's one-hot encode it. Let's introduce a whole bunch of binary dummy variables, and let's draw regression trees from the prior. And these regression trees are going to have the following form. You might split on the first coordinate, and then the second, and then the fourth. But recognizing that what x1 really represents is the value of the single categorical predictor. And so even though this regression tree does sort of partition the sort of unit square, it also partitions the discrete set that contains the values that your original categorical predictor can take on. And so what I've done is I've redrawn this tree, and I've illustrated the partition on the values that the categorical predictor can assume. And what we have is that at the root, we might split on x1. Well, if x1 indicates that x is equal to the first level lambda1, the decision tree is going to take lambda1 and put it off to the right and keep everything else to the left. And then it'll pull out lambda2, then it'll pull out lambda4. And so this recursive partitioning by removing one element at a time from a set is going to ensure that regression trees drawn from the BART prior will always form partitions of a discrete set that look kind of like this. They'll have a bunch of singletons, and then they'll have one set containing everything else. And there turns out to be 2 to the L minus L such partitions. And while this number is pretty big, it turns out to be like orders of magnitude smaller than the total number of partitions of all of the elements of a set. So to give you an example, if we had only 10 levels of a categorical variable, the BART prior is going to place positive probability on about 1,000 partitions of the values of that categorical predictor. But that's less than 1% of all possible partitions of this space. And so what this means is that the BART prior, when it comes to modeling categorical predictors, it's actually putting 0 prior probability on the vast majority of step functions that you can define over the relevant covariate space. And this means that it severely restricts the representational flexibility of the BART ensemble. And so what we're going to do, I don't want to do the sort of the technical bits. The point is that we need to create regression trees that sort of look like the following. The idea is that maybe we have a continuous variable and a categorical variable, and we'd like regression trees that will sort of be able to split on categorical variables and send multiple values to the right and multiple values to the left. And then maybe they subsequently split on continuous variables and then again on categorical variables. The point is we need something a little bit more flexible. And so what we ended up doing is implemented trees that sort of support this. And to give you an illustration in the context of Philadelphia, the original BART prior sort of create step functions that kind of look like the ones here on the far left. They'll sort of take a single census tract or maybe 2 census tracts and separate them out from the rest. And these types of step functions are going to have no hope of sort of modeling any type of spatial smoothness. They're going to over smooth across the entire city. We, in our first implementation, to just allow multiple levels of a categorical predictor to go to the left and the right in sort of a uniform fashion, that tends to produce partitions of the census tracts that looks like what's here in the middle. Now, while we can separate sort of the green cluster and the gray cluster, or the orange and the blue and the gray, you'll notice that these are not spatially contiguous. While you are able to borrow strength across different sort of cluster spatial regions, you're not doing it in a sort of spatially smooth fashion. What we really need to do is come up with a prior that will allow us to recursively partition all of the census tracts in the city into things that look like what's on the far right, where you've got sort of spatially adjacent things that are clustered together. It sort of allows you to model things spatially smoothly. And this is sort of the process that we built. So we have to figure out a way to recursively partition structured categorical predictors. And the way we do this is with the following stochastic process. So if we're at a decision node in the regression tree, we look at all of the values that are available to a categorical predictor. We look at the subgraph of some network that's induced by those levels. We draw a spanning tree of that graph, and we delete an edge. And this will always partition a graph into connected components. And so we bake this into the BART prior. Whenever you have sort of a spatial variable or sort of the census tract level, we always can derive a network, and we can always recursively partition it using this process. I know I'm very short on time. This is sort of the most boring slide of the talk. the thing that I'm proposing, it works better than all the things that we tried before that. And so what I'll leave you with is that, the sort of takeaway message is that when you have categorical predictors, and especially if you're building treed models, there's no reason to one-hot encode them. There's no reason to turn them into binary dummies. We have a way to do this in BART that allows you to even include structure amongst the levels to sort of co-cluster certain levels of a categorical predictor together. We're experimenting with different ways to do the network splitting. We have a preprint that just came out. You're welcome to check it out. I'm very happy to take any questions, either online or offline. And I just want to say thanks for taking your morning to hear about BART.